Okay, so let's try to find the power function. So power function for the previous example is defined for two unknown parameters, mu and sigma square. So in that we are using the rejection procedure that we have, which is T0, which is x bar minus mu 0, divide s over n minus 1 less than t, n minus 1 if over 2 given mu and sigma square, plus we have the reverse where t0, which is this one, s over square root of n minus 1 greater than now t n minus 1 if over 2 given mu and sigma square. Okay, so under this condition, we have to define the distribution of x bar minus mu 0 over s over n minus 1, where our true mu value, mean and variance are mu and sigma square. So here we have to define a different distribution. So you don't know the distribution yet. So let's see how to derive the distribution of x bar minus mu 0, where actually our mean is different than mu 0. Okay, so for that I will introduce you a new distribution, which is known as non-central t distribution. We will also see non-central chi-square and non-central f distributions. So how we derive the t distribution? If you remember, let's assume that we have a standard normal distribution and we have a chi-square distributed random variable, and let's say the degrees of freedom is just k, and let's say these two are independent from each other. Then we define our t by taking the ratio of x1 and in square root x2 and k. And we know that this has k degrees of freedom, t distributed with k degrees of freedom. We can consider the square of this as f1 and k. And if our numerator is not standard normally distributed, let's say it is distributed with mu and 1, and denominator same, let's say, and again these two are independent. In this case we have a different scenario and the same ratio. We are not changing anything. Okay, so we are using the normal distributed random variable where mu is different than 0 case. So this is known as a non-central t distribution. So under this case, so this has a normal with mean mu and variance 1. So this part is different than 0. So on that, under this case, this t distributed as non-central t with k degrees of freedom, and we have some one non-centrality parameter, which is the mu value that we have here. Okay, so this is the non-central t distribution, and this is a non-centrality parameter. And we have some table values, charts for non-central t distribution, so we can find the probability values using these charts. Okay, so as you can see, we have a similar situation. In our situation, we have x bar, which is distributed as normal with mean mu and variance sigma square over n, right? And we have n s square over sigma square. Emily we are using Emily as s square, which has chi square with n minus 1 degrees of freedom, and these two are independent from each other. So when we focus on the numerator part, when we consider the subtraction of x bar and mu 0, what we have here is normal with mean mu minus mu 0 and sigma square over n. Right, and then to be able to get rid of the variance part, you have a unit variance. What we are doing, dividing by the standard error, and we ended up with this one. So we have a normal distributed random variable. Okay. square root of n, we have now mu minus mu 0 divided by sigma and 1. Okay, so RT distribution coming from this part actually. So when we consider the ratio of this one, and this one, we will end up with RT 0 value. So square root of n x bar minus mu 0 divided by sigma, and we have n s square sigma square divided by degrees of freedom, and terms will cancel out, sigma squares will cancel out, so this will be r theta 0. Okay, so we will have x bar minus mu 0 divided by s and n minus 1 in square root. So using the procedure that we used for non-central distribution here, we have the same. So we have a non-central t distribution here with n minus 1 degrees of freedom and non-centrality parameter. So we define the non-centrality parameter with this quantity, where delta equals to square root of n mu minus mu 0 divided by sigma. Okay, so this is how we derive our testing procedure, and when sigma is unknown, we can replace it by s. Okay, then numerically we can find probability values. Similarly, to be able to get the power function of the previous example, this information is enough, but let's focus on other cases. So let's say we have x1 distributed as chi-square with k1 degrees of freedom, and x2 distributed as chi-square with k2 degrees of freedom, and let's say these two are independent. Then when we consider the ratio of this, we will have an F distribution. You already know that. We already derive it by using transformation, remember. But let's say we have x1, which is standard normal. Then the square of that will be chi-square with 1 degrees of freedom. But if our x1 is non-standard normal distribution like that, then the square of x1 is now non-central chi-square with degrees of freedom 1 and non-central parameter mu. Similarly, if we use the same procedure for the F distribution derivation, when we have a non-central distributed chi-square random variable and x2 denominator is central chi-square, these are independent, then we have a non-central F distribution. So the same ratio will give us a non-central F distribution with these parameters, degrees of freedom and non-central parameter, delta. Okay, so using this information, then we can define our power function. Okay, mu and sigma square. Then our T0 is distributed as non-central T with n minus 1 degrees of freedom with delta. We will give the delta later. And n minus 1 if over 2 plus non-central T delta. There should be no comma. Greater than t n minus 1 if over 2, where delta equals to square root of n mu minus mu 0, previously we defined it, remember, and this can be computed from non-central T distribution chart using degrees of freedom, non-central parameters, and alpha term. Okay, so this is how we derive the power function. So you have to be careful in some calculations of power function. Sometimes immediately we can find it, where like the case where the sigma is known case, but when sigma is unknown case, the power function calculation is also very different. Okay, so let's focus on a different question. So in some questions we have to use this testing procedure. We have to kind of draw the graph of certain functions to see which regions are the rejection region. So this is the type of question that we will use here. So now I will use a one-sided test because the procedure, the finding the likelihood ratio under the one-tailed test or one-sided composite hypothesis case is a bit different. So I want you to learn the logic, how we find the maximum likelihood values. So let's say we have a random sample of size n, and let's say we are testing that theta equal theta 0 versus theta greater than theta 0. It can be less than also, whatever, but also not equal to case, but I want to focus on the one-sided case right now to show you the procedure. Okay, and an A, let's say, find the generalized likelihood ratio lambda for this test in terms of x bar over theta 0 and also the sample size n. Okay, so to be able to find lambda, we need to define the maximum likelihood estimators under the parameter space. So we have to define our parameter space. Not regularly, our parameter space for exponential is all positive real numbers, but our parameter space for the test is different. So focus on this part. So for the hypothesis, our testing the region parameter space is theta greater than or equal to theta 0. So not just theta greater than 0. And under the null, our value for parameter is just theta 0. So we have to be careful because we need to find the maximum likelihood estimator where theta is greater than theta 0, not just theta greater than 0 case. Okay, so let's find this quantity. This is the maximum value of the likelihood function under the case that theta greater than equal to theta 0 case. So you know, for exponential, our MLE of theta is x bar, where theta is greater than 0 case. But where theta greater than theta 0, we cannot be sure that our x bar is greater than or less than theta 0. So we have to consider this fact. So let's say we have theta. Let's draw our likelihood function. So it will have a peak value at theta hat, which is x bar. Okay, so this will be the maximum point that the likelihood function can get. But sample to sample, this x bar value will differ, and whatever the value of theta 0, our x bar can be greater than or less than this given theta 0 value. Okay, so what is our region that's defined in the parameter space? Theta greater than theta 0 case. So if we have the case where x bar is less than theta 0 case, our parameter space will be this area. Then the maximum point that the likelihood function can take will be L theta 0, because the likelihood function drops after that. But when we consider the case that theta 0 is less than x bar case, this case, so the maximum value that the likelihood function can get, because we are using this region, so maximum point can be obtained at Lx bar. Then we have to define our maximum likelihood under the whole parameter space in two regions. So we will get L theta 0, where when my x bar is less than theta 0, and I will get Lx bar when my x bar is greater than theta 0. I will put an equality. I will show you the step where I put an equality sign. So I know the maximum point under the null because it only takes one value. Okay, then my likelihood ratio is the ratio of these two cases. Okay, so I have to define L theta 0 over L theta 0, where x bar is less than theta 0 case, and L theta 0 over L x bar where x bar is greater than theta 0. So here this ratio is 1. Our lambda should be between 0 and 1. There is no equality, okay? Because of that, we have to omit this case. So where I put an equality sign is here, because I don't want to have an equality sign in the rejection region. Okay, so my ratio will be this one then. Okay, so this is my constraint, so I have to keep this constraint with me till the end of the solution. So my likelihood ratio will be then L theta 0 over L x bar, and x bar is greater than theta 0. So what is the ratio? Then 1 over theta 0 to the n e to the minus summation xi over theta 0 over 1 over x bar to the n e to the minus summation xi over x bar. And actually, if you focus on this part, summation xi can be written as n times x bar over x bar. So what we have here is x bar over theta 0 to the n. Again, write this summation xi as n times x bar, and we have e to the. So this x bar values cancels out. We have minus n, and as a numerator it becomes positive, minus n x bar over theta 0. And we have x bar greater than theta 0 case. Okay, so our now likelihood ratio, lambda, let's write it again, x bar over theta 0 to the n, e to the n minus n x bar over theta 0. And we have our constraint. Let's write it in terms of x bar over theta 0 again. So in the question, it's asked that find the likelihood ratio in terms of x bar over theta 0 and n. So we accomplished that. And part B, determine the rejection region. Okay, so what is our rejection region? Reject H0 if lambda less than lambda 0. And we have this constraint with us. Okay, so we have x bar over theta 0 to the n, e to the n minus n x bar over theta 0. And x bar over theta 0 greater than 1. Let's take an ln of both sides, and ln x bar over theta 0 plus n, and x bar over theta 0 less than ln lambda 0. And we have this, greater than 1. Okay, let's y equals to x bar over theta 0. Now our statistic here is x bar or x bar over theta 0. So our function is based on this x bar over theta 0 value. So let's write our function in terms of y, n ln y plus n minus n times y less than k. Okay, and y greater than 1. So our rejection region is this one, but we have to write this rejection region in terms of y. Okay, so try to write this rejection region in terms of y. So how can we keep y alone? We have ln y and y. It's not possible to write y alone. So what we are doing in those kind of things, we try to get the shape, get some idea about the shape of this function. Okay, so this function is just z. So we want to get, we want to see some constant. Actually, so let's write this quantity again, n ln y minus n y less than some quantity which is k minus n, or let's put k prime here, then k. Okay, we get rid of the n term. So let's say this is our function z, and let's try to understand the shape of this function. It has a minimum, it's maximum, where this z is less than k. So our rejection region, reject A0 if z less than k. So what we are trying to do, write this in terms of y less than some quantity or less than or equal to some quantity, or two-sided regions, to be able to see that. Let's take a derivative of the function to see we have a minimum point, maximum point, or a saddle point. Okay, so we have z, it's the function of y. Take the derivative of z in terms of y. So what we will get, ln y minus n, equate this to 0, and we get the value of y equals to 1. So we don't know at this point it's maximum point or minimum point. Let's take the second derivative. Okay, so minus n y squared, and when y equals to 1, we have minus n, which is negative. So this means that this point gives us the maximum. Okay, so let's draw the shape. So let's say this is our z, this is our y, and when we replace this 1 into the function z, ln y, ln 1 will be 0, and we will have minus n. When we replace it by 1, we will have minus n actually. So we will have such a shape. So we have a negative quantity, and this is the point where y is, this is the minus n part. And what is our rejection? This part is not important actually, the position or how you draw the shape, but the important thing here is your rejection region in terms of k. So let's say our k is somewhere here, okay, and my rejection region in terms of z is less than k. Okay, so this region is my rejection region. I'm trying to write this region in terms of y. So in terms of y, okay, so this point less than this point and greater than this point will be my rejection region. So this is the point where we have 1, we have k1, and we have k2. So this will be the rejection region in terms of k's. But if you remember, we have one constraint, right, in the rejection region. So reject H0 if z less than k and y greater than 1. Remember our constraint? So here y greater than 1k. So our y should be greater than 1, right? So this region should be my case, and in terms of rejection region, this region should be my rejection region. Then I have to get rid of this one using this constraint. Okay, then previously we have two-tailed tests. If you look at this region, I will reject null hypothesis where y less than k1 or greater than k2, but using this constraint, now I have a one tail test. Okay, if you forget about this constraint, then you will end up with two-tailed test result. Okay, so it will be wrong. Then my testing result procedure will be reject A0 if y is greater than k2. Okay, so now I get the rejection region in terms of y, and now only unknown thing is k2 here, so I have to find the value of k2 again. Yes, again using the value of alpha. Alpha is given to us, and probability that the rejection region where y greater than k2 where theta equal theta 0. So what is y? It is x bar over theta 0 greater than k2 given theta equal theta 0. So now we have to define the PDF of this. Or if you can convert this PDF to a distribution or a random variable which has a standard statistical tables, then we will convert it. And we started with exponential, and as you can guess, we will end up with chi-square. Okay, so x distributed as exponential theta. This means that x bar distributed as gamma with n and theta over n, and this means that multiplying x bar by 2n and dividing by theta, we have a chi-square distributed random variable with 2n degrees of freedom. So apply this to our alpha function, probability that 2n x bar over theta 0, because my theta is actually theta 0. It's stated like that, it's given as a condition. So we have 2n k2. Given theta equal theta 0. After writing the distribution, we don't have to write the conditions anymore. 2n k2. So now I have to find the value of that. So consider chi-square distributed random variable here, chi-square 2n, and I want to find the value 2n k2, where my chi-square random variable greater than that gives me this alpha, very small probability. So I'm talking about the upper tail probability here. It is like 5%, 1%, whatever that is. So this point is this one. In terms of chi-square, so you know the value, it is 2n degrees of freedom. I am using the upper tail probability here, alpha. Then I can define my k2 as chi-square 2n alpha over 2n. So my likelihood ratio test of size n will size alpha, not n, sorry, reject H0 if x bar over theta 0 is greater than chi-square 2n alpha over 2n. Actually, if you remember the testing procedure that we developed using the uniformly most powerful procedure, where we find the maximum likelihood ratio statistic, monotone likelihood ratio statistic, and then using the direction of the alternative, we quickly find the direction, and then we define our tests as this quantity. Remember, we ended up with the same test, but using the likelihood ratio procedure is very long, and we ended up with the same. But for some cases you have to use this procedure because we don't have any UMPT cases, so you have to know how to construct the test based on that, and you have to be careful about using the constraints and using this constraint till the end of the procedure. Otherwise you will end up with the two-tail test, and all the testing procedure will be wrong in that case. Okay, so let me stop here. Then we will continue next week with the likelihood ratio test again, using the distribution of asymptotic distribution of likelihood ratio, and also we will consider the cases where we have two sample cases. So it will be very long actually, the solution of the two sample case. And after so next week we will finish likelihood ratio concept. Then the second week or the third week of April we will discuss the sequential probability ratio tests, and after that we will focus on Bayesian estimation, point estimation, and also confidence interval and hypothesis testing procedures in a very basic level, not a hard one. So actually after this week we will have 3 weeks to finish all subjects. Then we will finish everything. So if you want we can solve some questions, but after 3 weeks I'm not counting this week, or counting with this week. In 4 weeks we will finish all the topics. Okay, so try to understand the concept here. I know it's a very hard topic to understand and follow everything. So we will meet on Wednesday at 11 a.m. So if you have any questions, you can ask me there, or you can send me an email. So we can arrange another one-to-one meeting if you want, or I try to explain everything via email. Okay, so take care guys. See you on Wednesday.